Hello all, welcome to section 2.3, and we're going to continue with our discussion about functions, and we're going to talk about different properties that functions have. So let's take a look at today's topics. We're going to determine whether a function is even or odd just by looking at it on a graph. And then we're going to be able to do the same thing by looking at just the equation. We're going to use graphs to determine where a function is increasing, decreasing, where it's constant, and how to find the local max and min. We're going to be able to locate an absolute max and min as well as a local max and min. And then we're going to wrap up today by finding the average rate of change of a function. So the first topic we're going to look at is even and odd functions just by looking at a graph. So first thing first, let's take a look at a quick definition. So definition 1 says a function f is even if for every number in x, its domain, the number minus x is also in the domain. So what does this look like? So it is basically if f of x is equal to f of negative x. So if I were to put a negative x in everywhere that there's an x, you're going to get the same answer. Now, on the other hand, it's odd if for every number x in its domain, the number minus x is in the domain. So this is slightly different. So now if I put in a negative x every time I see an x, I'm actually going to get a negative of the original function. So the definitions are kind of similar, but let's see what this actually looks like in practice. But first, let's take a look at a theorem. So a function is even if and only if its graph is symmetric with respect to the y-axis. Okay, so let's think about that y-axis. That's that one that goes up and down, that vertical. If it is symmetric on either side of that axis, it is even. Now, on the other hand, a function is odd if it's symmetric about the origin. So if I were to take an imaginary line and put it at the origin and be able to do a flip-flop, then it would be odd, and if it was exactly the same on both sides. So let's look at some examples of what this looks like. So here we go. We're going to do it by looking at these graphs. So determine whether each graph given below is the graph of an even function, an odd function, or a function that is neither. Okay, so on part A here, if you remember, we said, and I'm going to write up here in the corner, even it's with respect to the y-axis. So if I take the y-axis here and I look on both sides, this is symmetric about that axis, okay? If I were to fold it right on this line right here, these would be identical. So that means that this one is even. I can tell that just by looking at the graph because, like I said, if I fold it along that y-axis, then we're, good to go. Now, number B, that works, okay? If I were to fold it on the y-axis here, is this going to be symmetrical? So it's not even, okay? Because if I were to fold it, it's going to be not symmetrical. They're going to be completely different. So it's not even. Okay, so now let's look with respect to the origin. So if I were to look here, and I'm looking this way, if I were to fold it like that, is there anything? No. Okay, it's not even, it's not odd. Okay, it's still a function because there's only one point going left to right, but it's neither even nor odd. Now, if I were to look at this last one, let's look at the y-axis first. If I fold here, it's not even. Okay, so if I fold here, this side is not equal to that side. Let's do it like that. Okay, not equal. So it's not even. But now if I were to take this point here at the origin, and I were to look this way and this way, it's odd. Okay, so even, it's going to be around the y-axis as in A. Odd is going to be about that origin point at the center, okay, like in C. And you can have ones that are neither even nor odd. Let's take a look and let's look at equations and see if we can do the same thing we just did by just looking at a graph, but with an equation. So we're going to look at, oh my goodness, I don't know why when I use this, it doesn't like my equations here. There we go. So we're going to look at these 4 different equations and we're going to determine whether it is an even, odd, or neither. And then that is going to help tell us whether it is symmetric with respect to the y-axis or the origin or neither. So let's look at that first one first. F of x equals x squared minus 5. So if it is going to be even, we said that f of x is going to be equal to f of minus x. If it is going to be an odd function, we are going to say that f of minus x is going to be equal to the negative of f of x, like that. Okay, so let's put our little box over here. So let's put our box over here so that we remember those equations. Okay, so to determine whether this function is even, odd, or neither, the easiest thing that we can do is replace x with the negative x, because we can see it, we can do it here and here. And then what we see if our result is that one or that one, okay? If it's neither, then the answer is neither. So let's go ahead and put a minus x. So f of negative x is going to be equal to negative x squared minus 5. Now, negative x squared is the same as saying x squared. So f of minus x is going to be equal to x squared minus 5. Now, if we look, f of minus x is going to be equal to f of x. Okay? Now, let's look at our rules over here in our box and see what that means. So we've got that first one. So it means that it's even. And when we looked at the even function in the graph, we know that those are symmetric about the y-axis. Okay? So that one comes out as even and symmetric about the y-axis. Let's look at the second example. G of x equals x to the third minus 1. Now, remember, even, f of x equals f of minus x. Odd, f of minus x equals minus f of x. Okay? So let's do the same thing again. Let's put in that minus x into g of x. So g of negative x is going to be equal to negative x to the third minus 1. Now, a negative to the third, it's going to be a negative number. So that's going to be a negative x to the third minus 1. G of negative x equals. Okay. Now, we can take a look at this and say it's not even because it's not equal to g of x. Okay. And minus g of x is going to be negative x to the third plus 1, okay? So that's also not equal to g of minus x. So it's not odd, okay? So it's not even, it's not odd, it's not symmetric, M-E-T-R-I-C, about anything. About the y or the origin. Okay, so it's not symmetric about the y, it's not going to be symmetric about the origin. Okay, let's look at the next one. So now we've got h of x equal to 5x to the third minus an x. Okay, I'm still going to put my even and odd. F of x equals f of minus x. And my odd is f of minus x equals minus f of x. I'm going to keep making them a little bit smaller, so maybe by the last one we don't have to write it again. How's that? Okay, let's figure out what h of minus x is going to be. It's going to be 5 times minus x to the third minus a minus x. Okay, let's take it piece by piece. We're not going to go fast. Let's look at, let's look at that first term first. A negative to an odd number is going to keep it negative. So that's going to be, let's pull it out in front of the 5. So minus 5x to the third. And we've got 2 negatives, so it makes it a positive, plus x. And that's what h of minus x is. Okay. So we can see right away that it's not even, because that does not equal h of x. Okay, but let's take a look at what minus h of x is. So let's put a negative in front of the 5. We're going to do this, 5x to the third minus x, and we'll distribute that minus sign. So we get minus 5x to the third plus x. Okay, that equals what we just figured out up here. Okay, so it is in fact odd. Because it's odd, we're saying it is symmetric about origin. Okay, that's all there is to this. Okay, you put in that negative x in for x. If it's even, we'll know because it equals the original. If it's odd, it is the negative of. Okay, one last example on this, and what we're going to do is we're going to throw another wrench into the basket. So I'm not going to put our even and odd up in the corner, but you can do that if you want to. So let's determine whether the function is even, it's odd, or it's neither. So let's put in that minus x. Now, what does absolute value do? So absolute value is going to wipe out whatever sign is in the front and always make it positive. So it doesn't really matter. So in essence, what we're saying is f of minus x is always going to be equal to the same thing as absolute value of x, right? Because it doesn't matter whether you have a negative in front or a positive in front. It's always going to come out the same. That is equal to our f of x, okay? If our f of x is equal to f of negative x, we are going to say it is even. And if it is even, where are we symmetric about? The y-axis. Okay. Don't let things like the absolute values, catch you up. Don't let things like, squares and cubes mess you up. Just take it piece by piece. You'll be fine. Let's look at graphs, and we're going to determine whether a graph is increasing, decreasing, or constant. So increasing means it is going up in value. So say you are going from 0 to 5, that is increasing. Decreasing means you're going down, so you're going like down in value, so from 5 to 0. And constant means you're just staying the same. So if you're always the number 3. So let's take a look at a graph, and this graph is going to have all different pieces of increasing and decreasing, and we're going to be able to go ahead and decipher each one of these pieces and figure out. So when we determine where a function is increasing and decreasing and where it's constant, we need to use strict inequalities involving the x variable, okay? Or we can use open intervals of the coordinates. So the function here is what we're going to look at. So the first one that we're going to look at is where it is increasing. So we're going to say it is increasing if we're going up the hill. Okay, so that is what increasing is. Okay, so as we march along from left to right, where do we see it going up? Well, here we're not, right? We're sliding down, but here we're marching up the hill here until we reach this point right here. Okay, here we're not marching up the hill. Here we're not marching up the hill. Okay, right now we're only looking at marching up the hill. So we can say, remember, we're going to do it in terms of x. So x is increasing between -4 and 0. Okay. You don't put or equal to because you don't know what's going on at that point. Okay, so it is just the less than. So that's one way to write it. Okay, that's writing it over the interval. Okay, now we can also write it as coordinates by saying it is open-ended, remember, because the square means we're equal to and we're not or equal to, from -4 to 0. And again, we're using the parentheses. So either one of those ways, depending on how the question is written. Okay, let's look at the same graph and we're going to look at where we're decreasing. When we decrease, we slide down the hill. We're going to go sledding. So decreasing is going down the hill. Okay, so we've got a point here. We're going down the hill. Now we've already said we're going up the hill here, so we don't want that one. Here, we're not sliding down, but we're not going anywhere, so we're just going to ignore that one. Oops. My lines are not straight. But here, we're sliding down the hill again. Okay, so we've got two separate areas where we're decreasing. We're sliding on this left and we're sliding on this right. Okay, so we need two sets of information. So let's look at part A over here first. So for part A, we are going from -6 to -4. Oops, I forgot my alligator. Or I can write it as this. Okay. So let's look at part B over here. How can I write this? I've got a 3 and I've got a 6. So I can say 3, 6, just like that. Or I can say 3, 6. So these are the spots where it is decreasing. You can have multiple areas. You don't have to connect to them anyhow. So if you're asked, you can say it's decreasing here and here. Okay. The last one we're going to look at, of course, is constant. So we've looked at most of these sections where they're changing, right? We're going to go here, here. Oh, this is the one that gives me trouble when I draw. There we go. That's not too bad. That we said was decreasing. That we said was increasing, so that's not it. This over here we said was decreasing. This right here is where we're staying constant. And if you notice, X is not changing, okay? I mean, I'm sorry, Y is not changing. Just ignore me, it's fine. Y is not changing. We are a straight horizontal line. So we can say we are from 0 to 3, from 0 to 3, or 0, 3. So we can say it is constant between x is between 0 and 3, or the coordinate 0, 3 on that open interval. Okay, so after we do all of that, let's go ahead and define exactly what we did. So a function f is increasing on an open interval if for any choice of x1 and x2, x1 is always going to be less than f2. Oh, x2. And we have f of x1 is less than f of x2. So if that y is going up the hill, and that means it's increasing. A function f is decreasing on the open interval for any choice of x1 and x2 if, as you're going from left to right, so your x is increasing, your f of x1 is going to be greater than your f of x2. Or in other words, we're falling down that hill like we do here. There we go. A function is constant over any interval for all choices of x, and no matter what x you're doing, if that f of x doesn't change. So that is going to be your horizontal line, as if you're constant. Okay, that's all there is really between the increasing, decreasing, and constant. So let's now move into looking at local, max, and min. So let's look at definition first. Let f be a function on some interval. So we've got something somewhere. That's helpful. A function f has a local max at c, and our c is here, if there's an open interval in L containing c. So for all x in the open interval, f of x is less than or equal to f of c. Basically, we're getting to the top of the hill. So it is increasing directly before it, and it is decreasing directly after it. That's a local maximum. On the other side, on the flip side, a local minimum is going to be where you are at the bottom of that hill. So everything leading up to it is going to be decreasing. Everything directly after it is going to be increasing. That is what we're going to be calling a local minimum value of f. So that definition, a function f has a local minimum at c if there is an open interval in L containing c, so that for all x, f of x is going to always be greater than or equal to c. So you can see here, c is going to be your bottom. So on either side, it's always going to be greater than or equal to. Here, you're going to have a top on either side. So it's always going to be less than, okay? Again, you could just look at it as the top of the mountain or the bottom of the valley, I guess. Not really sure. That's okay. We're going to look at this by doing another example, and we're going to find the local max and min from this graph. And we're going to also determine where it's increasing, decreasing, or constant. And we're going to take it step by step, A, B, and C. So for A, what values of X does F have a local max? And we're going to list those values. For B, where are their local minimums? And we're going to list those values. And for C, we're finally going to discuss which intervals are increasing and which ones are decreasing. So let's concentrate on A first. So let's pull A out. So what we're looking for is the local maximum. So the local maximum is the top of that mountain. So if we look on this left side, this continues on to infinity. So there's nothing there. Same thing on this left-hand side. I mean, this right-hand side? The right-hand side. It goes on to infinity, and it just keeps going on forever. Now, we do have some points here. Okay, we've got 3 here that we're looking at. Remember, we want top of the hill. So this one right here in the center is the top of the hill. Remember, we're looking for that top point. Okay, so there's only one. So the local maximum value is f of 1 equals 2, or the ordered pair 1, 2. That's your x and your y. Okay, it's increasing before, decreasing after. You can see right there on the picture. Let's move on to B and find where the local minimum is. So again, we've got those 3 points, and for minimums, remember, we're looking for like the bottom of the bowl. So here we've got a dip at the bottom of the bowl here, and we've got a dip for the bottom of the bowl here. Okay, so there are actually 2 local mins, okay, and they are at f of minus 1 equals 1, and f of, we're going to do that one, f of 3 equals 0. Or they're at points minus 1, 1, and 3, 0. Okay, so you have 2 local minimums happening. So let's look at that part C, the intervals of which it's increasing and decreasing. So we've already picked out those 3 points, right? 1, 2, 3 as locals. And by definition, we can say it's either increasing or decreasing on either side of those, right? So let's see, which one should we do first? Let's do increasing first. There we go. Actually, you know what? We can do them together. Decreasing. Okay. Because what I'm going to do, I'm going to start this way. I'm just going to work my way this way. And we'll put it into whatever column it belongs in. Okay. So as we're marching along, we're falling down the hill. Okay. So for decreasing, we are starting over here at negative infinity, actually. Okay. So it is decreasing from negative infinity to where? As I'm marching over to -1. Okay. That's my first decreasing. Okay, so now we're going to be starting at -1 and marching. Now we're going up the hill, so that's increasing. So we're increasing from -1. Okay. And where am I going to? I'm going to 1. Okay. After that, I start sliding down my hill again, so I'm decreasing. So I'm going from 1. Okay, I'm decreasing, decreasing, decreasing. I'm getting to the bottom. That's where I changed. So from 1 to 3. And then here again, I'm going out to infinity. So I'm increasing because I'm going up the hill. And I'm starting at 3 and I'm going to infinity. That's how I find where I'm increasing and decreasing. Now I can also write that in the other format by saying x is less than -1 and x is between 1 and 3. Okay, or I can say x is between, oops, let's try that again. Haha, x and 1 and x is greater than 3. Okay. That's how I tell where it's increasing and decreasing at. Next topic, let's find an absolute maximum and minimum. So let's first take a look at what the difference between the local minimum and maximum and an absolute minimum and maximum is. So this is a graph here, and you can see the difference already. The graph we just looked at had those arrows going off into infinity. This one is a very finite graph. There are points at each end. It's not ever going on to infinity. So let f be a function defined on our interval. If there's a number in there somewhere where f of x is always less than f of u, okay? So an absolute maximum is going to be the maximum of the maximums, okay? It is going to be the location on the graph that there is no question there are no other maximums that are higher than that one. Now, again, the absolute minimum is going to be the opposite of that. You can find all of the minimums on that finite graph, but it's going to be the minimum of the minimum, okay? So in the graph we had just looked at, we had a situation where we had 2 minimums. There were 2 local minimums. If we were to take the minimum of that minimum, that would be the absolute minimum. Okay, so again, let's go through a few different graphs and find the absolute max and the absolute min if they exist. And we're also going to talk about any kind of local maxes and mins that we find, just because you usually have to find those locals in order to find the absolute. So we're going to look at 5 different graphs here. We'll pull them each apart like we always do, but let's go ahead and start with graph A. So this is going to be a closed interval on 0, x equals 0 to 5. Okay, so x is going from 0 to 5. We have closed in dots, so we actually have them like that, or 0, 5. We changed to the square brackets because we are saying that it or equal to. So that's the domain. Okay. So over this domain, where can we see any maximum? So let's look at the maximums first. So we definitely have a maximum here. So we have a maximum. So let me write max. Okay. We've got a maximum at x equals 3, right? And we have, where's our absolute min? It's the absolute lowest value. It's going to be right there. Okay. Now, these are going to be my absolutes. Let's look for locals. Okay. We also can say that they are locals as well. X equals 3 is a local max. But where else do we have some minimums? Where do we have a local min? What about right there? Remember, we said decreasing on one side, increasing on the other. So we actually have a local min at x equals 4. Okay, so that's the local, that's the absolute. So you can see it is the minimum of the minimums. Let's move on to the number. Let's move on to letter B. Now let's look at graph B. One thing we do have to notice about graph B is our little open circle right there. So our domain is actually going to be the set of X where X is between 1 and 5 inclusive, but X cannot be equal to 3. Okay, because of that open circle. So notice we're getting rid of the 3 from the domain because of that little hole that we have at 3, 1. Now, our absolute max, okay, the highest of the high, is where? Is that X equals 5. Okay. Now, let's see. Absolute min is what? Well, we have to be careful because this is an open circle. We actually do not have any. Okay, why? So as you trace that graph from left to right, we're going this way, okay, you're decreasing as you're getting closer to this 3 and you're increasing after the 3. But when you're at the 3, it's not there. Okay, so there's no single value that you're going to say, oh, that's the smallest, that's my minimum. So, you know, as you get closer to that 3, 1, there is nothing. Okay, so because of that, there is no local min. Local min. But also for here, we don't know what's going on over here, so there's also no other local maxes. Okay, so this is really the only answer for this one. So pay attention to your dots, and in order to know if it's a maximum or a minimum, we need to know what's happening on both sides of it. So those ones at the end, we don't know what's happening after it, but we can use them for absolute, but not local. Again, let's go over to C, and let's see what is going on. Now we have all closed dots, right? So that's good. So our domain is going to be from 0 to 5, or square brackets 0, 5, and they're square because we have the equal to. Okay, our absolute max is the absolute maximum value. Oh, wow, that line's not even straight. Just try that one. Okay, is it x equals 5? Our absolute min. Okay. Now, notice what's happening here. We actually have 2 points, and everywhere between that, it's a minimum. Okay, so the minimum is actually occurring over an interval, and that's okay. So we are going from x equals 1 to x equals 2. okay? Or we can do it as 1, 2, okay? That's okay. You can do that. It's fine in order to have an absolute minimum or an absolute maximum over an interval. So this one actually goes between those different x's, okay? Now, the function has a local minimum value everywhere between this one because there's different values. That's also your local min, and there's no local max. Again, this is not a local max because you don't know what's going on the other side of it, okay? You can use them for absolute, you can't use them for local. Okay, let's look at D. We should be getting pretty good at these by now, right? Domain. Okay, we don't have any open circles, but we have an arrow, okay? So what you have to say is x is greater than or equal to 0. Or you can say on the domain 0, infinity, square bracket. Now, is there an absolute min? Min? Nah, let's do max first. Is there an absolute max? Well, this keeps going on towards infinity. So we don't really know where the maximum is. So there is none. Okay. But an absolute minimum is here, right? Because it's only getting bigger from there. So where x equals 0. Again, because this is an endpoint and this one's infinity, there are no locals. No locals, absolute, at no absolute max. The last example, and then we're going to move on to the average rate of change, which I believe is the last topic. So let's look at this one. We've got a domain. Let's find our domain, D-O-M. Whoa, I've written it 50 times today and I can't remember how to spell it. That's fine. Okay, we've got some open circles, so that's going to be a problem. Now, remember, when you have the dotted line, it means that at x equals 5, that means it's going to get super, super close to that. It's never going to cross it, okay? So we can actually say that it's for all x on the, so that x is less than, okay, we're going to start at 1. It's an open, so we have no equal to x, okay? And here we never get equal to that 5. Okay. Now, we have to take into account that other dot right here. So x cannot be equal to 2. Okay. Now, let's look at absolute max and absolute min. So for my absolutes, do we have any absolutes? So the highest value we have here is 4, but we're never equal to it. Okay, so there's no absolute. As far as our min goes, we keep going on to infinity here. Oops, that's supposed to be an n. Min, yeah, that'll work. Okay, now, no absolutes, but what about locals? Okay, well, I have a bump a bottom here, but we never actually reach that. So there's no local min. I'm having problems writing the word min today. Okay. We've got a top of the mountain here. So I have a local max at that bump at the top of the mountain where x equals 4. So let's look at this theorem real quick. We're not going to really do any implementations. That's not a word. We're not going to implement this anywhere, but it's going to kind of explain what we did just a little bit. So if f is a continuous function whose domain is on a closed interval from a to b inclusive, right? Because we have the square brackets, so it means we're equal to, then f has an absolute maximum and an absolute minimum somewhere on there. Okay, there's got to be one somewhere in there as long as you are continuous. Remember, those open dots mean you're not continuous. So if you are continuous, and I believe the one that we did that was continuous is more like A and the graph of A that we just did. That's going to be continuous. It's got a complete line. There's no arrows. There's no open dots. It's all closed dots, and it's all lines. So there is going to be an absolute maximum and an absolute minimum somewhere on there. Okay. Last but not least, let's take a look at how we find the average rate of change of a function. And these are all related because your rate of change is going to be related to whether it is increasing or decreasing and how fast you're actually doing that increase or decrease. Now we have a definition here. Don't freak out on me, okay, please. If A and B, where A cannot be the same as B, so A and B have to be two different locations in the domain of a function, then y equals f of x, the average rate of change from A to B is going to be f of b minus f of a over b minus a, or the change in y over the change in x. This should look, ooh, look at this. This does not even look like what it's supposed to. F of b, f of a. Let's try that. A cannot equal b. I think that's right. There we go. Okay, beautiful. So what does this look like? We've already used that, okay? This is the same as your slope, your rise over your run, okay? Change in y over x, a change in x, okay? So we've got this graph here, and the average rate of change here is going to be different between whatever 2 points that you select on that graph. Okay, because remember, these graphs are not lines. So let's find the average rate of change of f of x equal to 3x squared over 1 to 3. So the first thing that we can see is that your average rate of change is your delta x over your delta y. I'm going to have to put those in for some reason. One of these days I'll learn to fix my slides. It's fine. Oh, let's say f of b, so from 1 to 3. So x equals 1, 2, x equals 3. Okay, so let's make this one a and this one b. Okay, so from our equation down here at the bottom, we have, on the bottom, we have b minus a. Okay, f of b is going to be equal to 3 times 3 squared. F of a is going to be equal to 3 times 1 squared. This is going to be equal to 3. It's going to be equal to 27. Okay, so let's put those two values on the top. So f of b is 27 minus 3, okay, which is going to be 24 over 2. It's going to be equal to 12. That's my average rate of change for that equation from 1 to 3. That's all there is to it. Okay. Another example of x equals 3x squared from 1 to 5. And remember, we've got delta y over delta x equals f of b minus f of a, b minus a. A cannot equal b. A is going to be equal to x equals 1. B is going to be equal to x minus equals 5. F of a equals 3 times 1 squared, which is just going to be 3. I'll be complete. How's that? My f of b is going to be equal to 3 times 5 squared. So f of b is going to be equal to 3 times 25, which is going to be equal to 75. Okay. Let's go ahead and put it into our rate of change equation. So f of b, so I've got 75 minus f of a, which is 3, divided by b, which is 5, minus a, which is 1. So I've got 72 over 4. And let's see, 4, 5, 6, 7, 3, 18. The answer is 18. Okay, let's do one last one. We've got the same f of x, okay, over the interval from 1 to 7. We've got delta x over delta y, or delta y over delta x, sorry. A cannot equal b. So a is going to be equal to x equals 1. B is going to be equal to x equals 7. F of a equals 3 times 1 squared. F of a is equal to 3 as always. F of b is going to be equal to 3 times 7 squared. So f of b equals 3 times 49. I get my calculator out now. We're beyond numbers that I can do within my head. 49 times 3, 147. Okay. Let's put that down into our equation. So f of b, 147 minus f of a, which is 3, divided by 7, which is b, minus 1. That's 144 over 6, which is going to be 24. Okay. That's all there is to it. It's actually quite easy. You just have to remember that formula, which is the same formula as what we used for slope. Okay, so average rate of change of a function is the same, kind of the same as looking for the slope. So let's take a look at this theorem. The slope of a secant line, the average rate of change of a function from a to b equals the slope of a secant. Now remember, a secant is kind of like drawing a straight line between those two points. So therefore, it is really just the same as finding the slope of that line. So you're going to have the points a, f of a, and b, f of b on that graph. Let's do the same thing and look at finding the equation of a secant line. Let me add my lovely things that don't like to show up with me here. G of x equals 3x squared plus 2x minus 1. Let's bring our equation in here. Delta y over delta x equals fb minus f of a, b minus a cannot equal b. And a cannot equal b because if you subtract the 2, then you have a 0 on the bottom. That's undefined. Okay. Let's say a equals x equals negative 2. G of a equals 3 times negative 2 squared plus 2 times negative 2 minus 1. G of a equals negative 2 squared is 4, positive 4. Positive 4 times 3 is positive 12. Negative 2 times positive 2 is a negative 4 minus 1. G of a equals 12 minus 4 is 8, minus 1 is 7. My b is going to be equal to x equals 1. My g of b is going to be equal to 3 times 1 squared plus 2 times 1 minus 1. My g of b is going to be 3 plus 2 minus 1. 3 plus 2 is 5, minus 1 is 4. Let's do our average rate of change equation. So g of b, which is 4, minus f of a, or g of a, which is 7, divided by b, which is 1, minus a, which is a negative 2. Don't forget to check your signs, okay? So 7 minus 4, 4 minus 7 is a negative 3. Okay, you've got two negatives, so they go positive. 2 plus 1 is 3. So my answer is a negative 1. Okay. So now we're going to say, suppose that g of x equals 3x squared plus 2x minus 1. Find the equation of the secant line containing negative 2 g of negative 2 and 1 g of 1. Now, this is different. So we just found the average rate of change between those 2 points. So the average rate of change, so the delta y over the delta x, was equal to negative 1 from the previous slide. We've got 2 different points here, and now we want to find the equation. So what we have here is we've got this right here. That's my slope. And I want it in the y equals mx plus b format, because we want the equation of that line, okay? So how do we do that? We can say y minus y1 equals m times x minus x1, okay? So here we can pick we'll pick this first one. It's fine because the answer is going to be, this is actually negative 2 and 7. We figured out this portion in the previous slide. So let's say y minus 7 equals negative 1 times x minus negative 2. Okay, we've got those negatives. It makes it a plus. Then we want to distribute that negative. Okay, y equals negative x minus 2 plus 7. I also did this in the middle. Okay. So we've got here, I'm going to come over here, y equals negative x plus 7, and a minus 2 is a plus 5. So that's my equation of that secant line. Next, actually last thing that we're going to do today, suppose g of x equals 3x plus 2x minus 1. Let's draw the graph of g and the secant line. So I'm going to apologize for my graphing inabilities right now. Okay, so we have 2 points. We have a negative 2, 7, and we have a, what was the other point that we had? We had a 1, 1, and what's 4? Okay, so 1, 1, 2, 3. There's 1 point. Okay, that's 1, 4. Negative 2, 7. There's 1 point. Now for the secant, I can just, or for the secant, oh, that is a terrible straight line. I can just draw the straight line. Okay. Now for the 3x plus 2x, okay, so we know it's going to go through these 2 points. Okay. And we're actually going to kind of do something like this. Kind of U out. Okay. Take a better look at what it's supposed to look like. Ta-da! That's so much better than looking at my scratchy drawings, but I was super close. So what you have here is, this is the equation that we figured out for the secant, and that's going to be that red line. This is the equation of the blue line, the original equation, and the rate of change between these 2 points is what this line is representing. Okay, so you kind of have that rise over your run of those 2 points. Okay, that's all there is for today. As always, if there's any questions, you can email your professors, and I will see you guys next lecture.